Hello, I welcome you all to this another interesting screencast. The problem reads, determine the shear force and moment at points C and D. And we'll say, and draw the shear force diagram and the bending moment diagram. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We have an overhanging, simply supported beam, a roller at A, therefore we expect a reaction force AY, and a hinge at B, therefore we expect also a BY, and a BX, like so. Let's apply the equations of equilibrium. So we have summation of moments about point B equal to 0. Okay. Alright, what do we have? We have a minus negative moment AY times 10, and then a plus 500 positive moment. No, this one is not times 10, this is times, that's a lever arm, this is times 14. Okay, 6 plus 4 plus 4, then plus 500 times 8, and then minus 300 times 8 equal to 0. Therefore, AY is just going to be equal to, let's find out, 500 by 8 minus 300 by 8 300 by 8 then divided by 14. AY is equal to 1114.29 if we rounded it off to 2 decimal places. 29 pounds. Okay, we check it out again. 500 by 8 minus 300 by 8 divided by 14. Great, 114.29. Alright, then what do we have? Then we have summation of forces in the y direction. Summation of forces in the y direction equal to 0. Going up in our reference, what do we have? We have AY minus 500 plus BY minus 200 minus 300 equal to 0. We already found what AY is. Okay, so we just replace it there, and once we do so, we'll find that our BY is just going to be equal to, so 114.29 minus 500 minus 200 minus 300, and this gives us BY equal to 885.71. Okay, 885.71. Alright, then finally we have summation of forces in the x direction. Of course, we know that this will just give us bx equal to 0 pounds. So let's include this information. We said by is equal to 885.71 pounds, and ay is equal to 114.29 pounds. Bx is just equal to 0 pounds. Great. So we are going to make sections at C and at D. So let's start at C. So if we made a section, let's draw the section. So we'll have something like that. We're going to use the left hand side of the section. So one that looks easy. We always go with a section with the which can easily be worked out in a shortest period of time. Okay, so we have 114.29. We have another force which is 500 pounds. All right, and this point is C. Okay, this length here from there to there is 6 feet, and then the length from there to there is 4 feet. Great. So at this section we expect a VC, MC, and NC. Okay, but we know NC already is 0, so there's no need. Let's just get rid of it. So let's apply the equations of equilibrium. So summation of moments about point C equal to 0. All right. What do we have? And then we have a minus 114.29 times the lever arm. That is from A to C, that's 10. Then plus 500 times the lever arm, which is 4. Then plus MC equal to 0. And therefore, our MC is just going to be equal to minus 114.29 times 10 plus 500 by 4. So this gives us MC equal to minus 857.10 pounds feet. All right. So let's find the other one. So we have summation of forces in the y direction equal to 0. Okay, what do we have? We have a plus 114.29 minus 500 and minus BC equal to 0. Therefore, our VC is just going to be equal to 114.29 minus 500. This gives us a minus 385.71 pounds. Great. So we are done with the first part. Let's make another section. So make the section at D, just there like so. At D, exactly at D. And which segment are we going to go with? We have the right hand side and the left hand side. Of course, we'll go with the simplest one, which is right hand side, of course. Great. So we are going with the right hand side. It's the simplest one. Okay, so that is a 300 pounds. This point is E, and then this point is G, and we have here a shear of VD and a moment of MD, and this length of this segment is 2. Alright, then we have summation of moments about point D equal to 0, and clockwise being our reference. What do we have? We have a minus 300 by 2 minus MD equal to 0, and therefore our MD is just going to be equal to minus 600 pounds feet. Okay, and then we have summation of forces in the y direction going up, our reference positive. We have VD minus 300 equal to 0. Therefore, our VD is just going to be equal to 300 pounds. Great. So we have found MC, one I'm just outlining in red, is negative. Just means the sign is in the opposite direction at that section. So it's negative. Okay. And our shear is also negative. Okay. And at section D, the moment is again negative. Okay. And at the shear also at D, the shear is positive. Alright. So remember issues of negative and positive, right? When a beam bends like this, our convention is the beam is positive, and when it bends like this, remember this, we say the beam is, bending moment here is negative. Okay. Right, bending where it's able to hold water. The beam, when it bends like this, it means it's experiencing a positive bending moment. When it spills off water, it means it has a negative moment. Bending moment, right. So we now want to draw the shear and the bending moment diagram. And we are going to use the two differential equations that relates the distributed force to the shear force and shear force to the moment. So the rate of change of moment with respect to x is equal to shear, and therefore moment itself is the area under the shear diagram. And the rate of change of shear with respect to x is equal to distributed loading, and the shear itself is the area under the load diagram. With these two equations, we are able to draw the shear force diagram and the bending moment diagram, which I feel maybe is sometimes much faster, especially when you have a lot of intervals, like in our case, if we had to do sections. Alright, but you can use whichever method is simpler, and if this works out simpler, then please go for it. We have plus and minus, and this is going to be our shear force diagram and our bending moment diagram. So let's begin to draw. So at A, so I need to include some information. We have A, B, and E. Let me put this one here as my F because I'll need this. Let me say F where we have a 500. Okay, so at A, we expect a positive shear. Let's say maybe up to somewhere there, like so, maybe up to somewhere there. So let's say this value is 114.29 pounds. And because from A to F, Q is equal to 0, which is we don't have any distributed force. Therefore, the slope of our shear diagram is going to be 0. So the 0 will just be a straight line like that. That line has a 0 slope. Up to there. Great. When it reaches where we have a point load of 500, the two will need to add up algebraically, considering the signs. So we are going to have a 114.29, which is positive, minus 500, which is negative. So when the two interact, we are going to have a value of minus 385.71. So 114.29 will be reduced by 500. So let's do that. So from here we expect a downward movement. Let's say maybe up to somewhere there. Let's say that is a 300. Okay, maybe up to there. This is enough. Okay, so let's say this is our 385. What did we say? This is our 385.71. Okay, then later on from F to B, we again know that Q is just equal to 0. Therefore, our dV dx, which is the slope of our shear, is also going to be equal to 0. So we are just going to have a line like this, which just represents a 0 slope. Great. When we reach where we have a B, we have By, and we also have a concentrated load at the same point. Okay, so we will need to sum up all that algebraically, considering the signs. Okay, so we have a minus, let's sum them up. We have a minus 385.71. Okay, then plus 885.71. Then minus 200 is equal to, so let's sum them up. Okay, so minus 385.71 plus 885.71 and minus 200. So what do we have? We have a positive 300, like so. Okay, so 385 will reduce and it will go to a positive 300. So let's move upwards. It will move from negative, or it will increase, not reduce. It will move from there, maybe go up to somewhere there. We can say that is our 300. All right, so what is that value? We said is 300 pounds. Okay, and then from there, from B to E, the Q is equal to 0. Therefore, our dv dx is just going to be equal to, our dv dx is just equal to 0. Alright, so our slope here will just have a 0 value up to e. When we reach e, we have another concentrated load there, and the two add up algebraically. So we'll have a positive 300 minus 300, just 1 minute, positive 300 minus 300 equal to 0. Okay, so this is going to close up like so. This will close up like so. Great. Alright, so we have drawn the shear force diagram, and we expect it to look like that. So that one is positive, this one is negative, and this one is positive. So let's look at what we found at C. At C we found a minus 385.71 negative. Great. And at T, let me just write this one. We say this is negative. Okay. And for D, section D, we found a 300 in this positive shear. Great. So everything is matching. Let's draw our shear force, our bending moment diagram. Let's just move this a little bit, maybe up to somewhere there. Okay. Alright. So what do we have for bending moment? Again, we are going to relate shear to the moment. So in interval AF, we have shear which is positive and constant. Okay, and then of course the slope for moment dm dx will also be positive and constant. So let's draw that. So from and this magnitude is just the area. This magnitude is the area under the shear diagram, which is just equal to 114, okay, 114.29 times 6, which is just equal to 114.29 times 6. This is equal to 685.74, and is positive. So at A, boundary condition, we don't have any moment, therefore we are starting from 0. That's important, and then our slope is positive and constant. So let's move there. Let's say we go to that point like so. Okay, so let's say that is our point. Let's say that is our point where we end, or where we go to. So we say this value here is 685.74. This is pounds feet. Okay, then from that end, from F to B, our shear is negative and constant, and therefore our dm dx is also going to be negative and constant. And this magnitude m is just equal to integral of v dx, which is just equal to minus 385.71 times the length, which is just a 10. So this just gives us a minus 338.57.1, a negative. Okay, No, it is multiplying by 8, sorry, not 10. This is 8, the length is 8. Alright, let me wrap that by 8. Therefore, let's multiply that. Minus 385.71 by 8. What does this give us? It gives us a minus 3085.68. Great. So here we are, our final value is 685.74, so they will need to add up algebraically. So we have 685.74 minus 3085.68. This gives us just hold on, I'm adding 685.74 minus 3085. Okay, so we have a minus we have a minus 2399.94. Let me check it again. 685.74 685.74 minus 3085.68. 2399.94. Okay, which is a negative. Alright, so this slope is going to move, is negative and constant, so we'll move from this point up to F, and it's a very big value, and we are lacking space up to, let's say, somewhere there. So I'll need to move this a little bit. I hope I'll have space. I need to move this as a whole. Okay, maybe something like this. Okay, it's fine. Yeah, something like this. Alright, then I'll need to replace information that has been distorted. Okay, here we had M, and yeah, we had M like so, and then this one was here 6 years like so. Great. So we are saying this value is minus, and not minus, of course it's already minus down there. This is 23, maybe it has gone so much down. Let me write it somewhere there. This is 2399.94 pounds feet. Alright, and then finally let's find this other part, the remaining part. So this other part, that is from B to E, Q is equal to, not Q, B is equal to positive and constant, and our dm dx is also positive and constant, and our M is the area under the shear force diagram, which is just equal to 300 times 8, right? 300 times 8. What does this give us? 300 by 8 gives us a 2400 positive. So these will need to interact. So we have a 2000, a minus 2399.94. Okay, right, then plus 2,400. What does this give us? Minus, we expected 0, of course, 2399.94 plus 2,400. We have a 0.06, which is just practically equal to 0 because of those round-offs that we are having. So we have a closure at this point up to there, like so. Okay. So this is our positive moment. This is our positive moment. And this is our negative moment. Okay, I think this is about it. This is about it. And let me just clean up this slate. This is about it. We have, let's check the moments at C. MC, we found a moment of minus 857, which is just somewhere. Okay, yeah, it's supposed to be 857, which we can check along this line. Okay, and then at D we found 600 minus 600 at the very end there. All right, yeah, I think everything else is fine. This one here can be rounded off. The one at the bottom, this can be round 23.99. We can round it off to 2,400. You've seen. Okay, this we can round it off to 2,400 pounds feet. Okay, great. So I think this is about it, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.